Morning, Monica. Can you hear me?
Yeah, I can hear you.
Good. Okay. Like we've finished up the Kirchhoff's rule problems there. And I want to give you I want to start off this problem with this lecture with a problem to kind of finish up resistance and get us into magnetism. And this is with a circuit analysis for RC circuits. So we've looked at capacitors, we've looked at resistors, and to finish up this chapter with looking at a chapter with resistors and capacitors in the same circuit. And I want to see if I give you an opportunity to work through the problem, try to set it up for you, and see if you can work through. Now, is there anyone in here who had me for Physics 37? I know David Edwards did. And anybody else? No? Okay. Well, this is a problem that you would have seen, mathematically, you would have seen it in that class. With drag. And it's a problem that I work out pretty extensively, spend a lot of time in class doing a mathematical technique called separation of variables to derive the kinematic equations for a force, object that experiences a drag force, either slow moving or fast moving drag. And I do it because that technique we use a lot, and this is one of the problems where it's necessary to use separation of variables. Let's consider what's called an RC circuit. RC circuit has both a resistor and capacitor. Now we're going to start off with a DC voltage, meaning direct current, so constant volt battery. When we get into magnetism, we'll look into AC circuits where voltage flips back and forth at a certain frequency. But for now, and there's a lot of interesting properties associated with RC circuits with that, but that's not yet. Here, we're just talking about battery with an M that will represent as like so. And we'll have a resistor and a capacitor in this circuit. Now, if we do a voltage analysis, we can go through, and in fact, why don't someone do that for me? Lucy, you want to try it? Why don't you start to help you out a little bit. Let's label some nodes here, or corners actually. Why don't you go from one counterclockwise, starting at clockwise, starting at position 1, and do a voltage, Kirchhoff's voltage rule, and add up all the voltages and give me an equation that defines the sum of the voltages around the circuit. Can we do that? Let's hear you there. Hello? No? Okay, yeah. Say again?
No, I was gonna ask, what do you ask?
I'm asking about, I wanted to apply, I wanted Lucy to apply Kirchhoff's rules to Kirchhoff's voltage rule to this circuit to give me an equation for the sum of the voltages around the circuit. But if Lucy's not there, you can give it a shot, Monica.
Would you have to use the definition for capacitance, which is, I guess, or the voltage, the formula,
Yes.
the voltage with capacitance and the charge,
Yes.
maybe?
Yes, you would. That's one that you would have to use, yes.
And then I guess the one for resistance, and do the
Yes.
same analysis that we did last time.
Yes, yes, that's right. So you have to use definition capacitance, you have to use Ohm's law, and then, of course, apply those using Kirchhoff voltage rule. Maybe Lucy stepped away. You wanna go ahead and do that for me, Monica?
Yeah, let me try.
Okay, go for it.
So I guess if we start 3.1, then we will do Q over C.
Awesome.
And then it will be negative I times the resistance.
Yes. Okay, keep going.
Positive E. Epsilon.
Then, yeah.
Equals 0.
Yes. Okay, wonderful, wonderful. Almost got it. One of the things that you need to be careful about is the polarity on the capacitor. If I have a switch here and I close the switch, what direction does the current flow, Monica?
To the left?
Yeah, counter or clockwise, yeah. So what is going to be the polarity of this pole of the capacitor? The left pole, or the left, yeah.
Positive.
Yes, that's right. This is going to be positive and the other one's going to be negative. So if you traverse that capacitor from left to right, as you did, that's V plus, that's V negative. What is going to be the polarity of the voltage Q over C as you go through that polarity, as you go through that capacitor?
Negative.
Negative. So there should be a negative sign here.
Okay.
So you have to evaluate that, right? Because a capacitor is just neutral until you put it in the circuit and then in a certain orientation for the relative to the battery. So you can't forget that. And for those of you who might have not realized what she was doing, we're using, as she had mentioned earlier, the definition of capacitance, right? Remember, capacitance is defined as Q over delta V. So then delta V, the voltage associated with a capacitor, is equal to Q divided by C. And the other one is Ohm's law. So this is definition of capacitance. And this guy is Ohm's law, delta V equals I times R. So we have to use these laws whenever we are, these definitions and laws whenever we're evaluating the circuit. Now, the other thing that I want to remind you of, I've been a little bit careful with the terms Q and I here. What is actually happening to this current in this circuit once I close the switch? Is it a steady state, meaning a constant current, or because I have a capacitor, what's actually happening to it? Remember when we talked about had the capacitor in the circuit alone, and we evaluated that, as the capacitor charges, as Q increases, what's happening to the current in the circuit? Anybody?
Decreasing.
It's decreasing. So I'm going to emphasize that these quantities now, Q and I, are actually time dependent. They're not constants anymore in a circuit like this. And in a certain amount of time, they are going to, the current will go to zero. The current's going to stop, just like it would if it were an ideal circuit with no resistance. Well, actually, that was even more of an ideal circuit. This is an ideal circuit in the sense that what we defined is that all the resistance is in the resistor and there is none in the wire here. But whenever we looked at the capacitor independent of the resistance, you know, I told you that was kind of a even more theoretical case because you got to have resistance, as we know with Ohm's law. If there's no resistance, the current won't flow at all. And when we were evaluating those circuits with just the capacitor, we were just doing that really ultra theoretical, right? Because it doesn't really make any sense. But now we're back to really considering that, you know, we do have a resistor there. And so the current is definitely flowing until it stops because of the nature of the capacitor. Yeah, so now this is a differential equation that can be solved. This is a differential equation. And yeah. So there are certain methods by which we can solve that differential equation and determine the functional form of the charge and of the current. Now, we really have two variables, charge and current. But in order to solve that differential, we need to get those, we need to have just one variable, which we can do by using the definition of current. Okay. Current is defined as Q of T is defined as, I of T, or current is defined as charge per unit time. So Q of T over delta T. And of course, in the limit, in the limit as delta T goes to 0 of Q of T over, and remember, this is really a delta Q as well, right? It's a delta Q technically, because remember how we defined current, it was a certain amount of charge going through a cross-sectional area. in a certain amount of time. So if we take the limit of that, what we actually have is the definition of a derivative from calculus. So we can really replace I with the derivative, with the first derivative with respect to time of Q. So if we substitute 6 into 1, then we have minus Q of T, or C, and actually a lot of people write it like this, so minus 1 over C, Q, T, minus D, dt, Q of T, plus the voltage across the battery equals 0. So that is a first order linear homogeneous differential equation. These types of differential equations may be solved with a method called separation of variables. Does anyone remember this separation of variables technique from differential equations or calculus 3 or maybe calculus 3? Might be 2. I don't know. I remember. David Edwards, how are you this morning? David, you there? David. Don't know if you all are hiding behind the camera or not. Okay. Dami, are you there?
Professor, I didn't hear what you said.
I was just asking if you were there.
Oh, yeah, I'm here. Yeah.
So do you remember, are you familiar with separation of variables? Have you had differential equations yet?
No, I haven't.
Which calculus are you in? 2?
Yeah.
Have you all done any work with solving differential equations? Calculus 2?
Yeah.
Okay. Well, I'm curious. Dami, did you also, what about, did you look at, do you remember your drag from mechanics? Did your professor study that? Or did you have me for mechanics?
Yeah.
Oh, okay. Well then, yeah, you should know it then. You remember when we did this, and I talked about, we did this with the drag problem. Do you remember doing that in
It was kinematics. I had your point. Physics 37.
Yeah. So do you remember doing the drag problem in that class? You remember doing the drag problem in that class?
To be honest, I'm not completely sure I remember.
You have your notes with you right now?
Okay. Let me check real quick.
Yeah. You have your notes with you, right?
Yeah, I still have my note.
Yeah, take a look. Look it up. you can follow through. I want to give you a few minutes for those who. What about you, Jason? Have you had, you separation of variables or all these questions, or do you know what I'm talking about? Have you solved differential equations like this before?
Yeah, you're supposed to multiply dt to the other side. So you're supposed to get q and dq on one side and everything else on the other side of the equal sign.
That's right. That's right. Why don't you all take a few minutes? I'm just curious. I want you to make a look. For those of you who can, take a few minutes, maybe 3 or 4 minutes, to see if you can at least make some progress with working towards solving this differential equation. Yeah. For those of you who might remember from mechanics, it would be like, so when when you have an object that's falling in air, there's drag. Drag is a problem. Drag is a force. Well, slow moving drag is equal to a constant k times the speed. So as the speed increases, the drag force increases. So if you look at a free body diagram, you're going to have mg down, acceleration due to gravity, and the drag force in the opposite direction. And of course, the object is accelerating or decelerating because it's increasing its velocity, so it's accelerating. So if you apply Newton's second law, net force equals mass times acceleration, then you've got, like mg minus drag is equal to ma. And that sets up and so you put in drag, so you have mg minus k times v equals m a. But a is also, is a derivative of velocity. So that's going to be a times dv dt. So you have a similar kind of scenario where you have something says first order homogeneous linear differential equation. Now I'll talk about that in a minute, what those terms mean if you don't remember. But you get something that's analogous to this. A constant, a first order derivative of velocity, and a zeroth derivative of velocity, or just velocity. So I could kind of shift that around a little bit. If I were to shift it around, it would look more like, so to get it in these same terms, it would be something like a minus k times v, then a minus m dv dt equals mg. And actually, I could probably go through and divide by m. If I did that, I would have an m here. This m would cancel. Yeah. So d dt v of t, and then plus g equals 0. Yeah. So that would be the same kind of, if you compare equations, so let's say 8, 9, 10, 11, 12. If you compare equations 12 and equation 7, you can see they have the same form. And so I went through, I usually go through, that's one of the problems you should do in that class, is go through it and solve that, show students how to solve it. Well, I do anyway. And now it's going to be in your book, but they're going to probably do it they don't go through all the steps and everything, usually. So that would determine that. That's velocity. So K over here, V of T. Yeah. Now, I'm going to step away for just a minute, but before I go, Give me a few minutes to work on that. But before I go, let's just say a word about these terms. So a linear differential equation applies to the terms of Q, where Q is there's no terms of charge that are squared. They're all Q to the first power. So that means that's what we refer to by linear. A homogeneous differential equation is when all of the variable terms like Q of t and d of dt, they're equal to a constant. In other words, if I take E and put it on the other side, then that's considered a linear, a homogeneous equation. If there are other terms over here that are variable, or it's kind of hard to explain, but in a math book, that's the way they would show it, that all the terms that have the differentials, the derivatives, are equal to basically a constant. Then that would be a homogeneous equation. Bring this back over here. And finally, first order means that the highest derivative of the equation is to the first power. So this is, d1 of q, dq of, it's the first order derivative of the charge is what I'm trying to say. And technically, d0 of dt0 is just 1. It's just, it's no derivative. Yeah. So whenever you have a differential equation that has these properties, then you can use this technique. And the technique is where you get all the one variable on one side, so all the Q of t's will have to be on one side, all the dt's will have to be on the other side, manipulate the equation that way, and then you integrate in order to find the solution to the differential equation. Yeah. So those of you who can, try to take a look at that for a few minutes. We'll be right back. Right. Making progress. Just come in Armando and AJ and Edmund. Folks came in a little late, so what we're doing is working through an RC circuit, the mathematics associated with that. Can't remember, Edmund or Armando, did any of you, or AJ, did any of you have me for mechanics or physics 37? Yeah. Did you, are you familiar with separation of variables technique? Armando. Okay, what about you, Edmund? Okay. So have you been able to start to work through, try to solve equation 7 with that technique? Okay. What about you, AJ? Are you there? AJ, Amar, Jelani? All right. Moving forward a bit. Well, I think the first thing we to do is separate the variables. So I'm going to separate them specifically based on a certain convention, which I want the answer to, anticipating a certain result from for the answer. Yeah, and I put a typo in there when I went back. This should have been plus. It was initially, and then I played around with the equation. And when I brought it back over, I dropped that plus sign. All right, so let's so I guess I really do need a little bit of space because I haven't used everything over there. So coming here, coming back to this equation, call this 13. I'm going to take the dq dt on the other side. So I will have did I make a mistake? Yes, I left out the R too. Oh my gosh, I'm kind of tired today, folks. I'm sorry. So this, I substituted the I into, the I equals dq dt into this, but there's an R there. So there's an R here, actually. So this term, dq dt, which is I, times R, plus the battery voltage as we come back around equals 0. So starting there, I'm going to take that term, dq dt, times R on the other side. So over here, I'll have the E, the minus Q over T, sorry, Q over C. And then on the other side, plus R times dq of T dt. So I've just algebraically solved equation 7, and that's 13. Now I'm going to divide equation 13 through by R. And that will give me equation 14. So I'm going to have E over R. Then I'll have 1 over RC, so minus 1 over RC times Q of T equals the derivative with respect to Q on the other side. Okay. Now here, I'm going to do something that is, yeah. I'm basically going to cross multiply at this point, because right now the variables are not separated. If you look, so the two variables are Q and T, or the two time-dependent quantities. Now, yeah. Yeah. If you look at a unit analysis, everything on this left side here really is associated with charge. So, right, this clearly is charge because it's Q, but this is kind of, if you think in terms of Ohm's law, right, voltage is equal to current times resistance. So current is equal to voltage divided by resistance. So this really is a charge with respect to time. It's basically like a, yeah, I mean, I know it's a time-dependent current, really, is what this is. So that's kind of associated with charge. I guess the point is that I can manipulate this a little bit. It's still not charge, actually, but I guess, yeah, well, okay, I guess that's not really a great justification. But I can manipulate this a little bit more. And I guess it's just algebra to get to that point. So one technique to do that is I'm going to cross multiply both sides. I'm going to take all this stuff for right now. And then I still have to do a manipulation, but all of that in the parentheses, I'm going to divide through that and then multiply through by dt. So I'll have a dt is equal to dq of t over all of that stuff. That's going to be an E over R. And this is kind of an interim step. So it really is just to get to my separation of variables. I could have done it in a couple ways you can do this, but this is just the way I do it. So now I'm going to divide out an RC here. Or yeah. So if I in the denominator. So if I do that, so I have dt over here, dq. I'm going to drop the time dependence of the charge just for notation purposes, just so to write so much. Now, if I factor, and actually I said factor out an RC, is actually factor out a 1 over RC. I have 1 over RC in the second term. If I factor that out, I'm going to have 1 over RC times quantity. Now, I'll have to multiply this voltage E times a C, right? Because if I multiply back through by 1 over RC, that's going to give me E over R. And over here, I just have Q of T. Okay, so now there you can see everything in parentheses has units of charge. Because if you look at this term here, E times C, that's also similar to that comes from the definition of capacitance. Capacitance is equal to charge over voltage. Right. Yeah, so charge is equal to voltage times capacitance. So this thing has units of charge, that has units of charge, obviously. The differential is in terms of charge. And so I need to get this thing, this RC over on the other side. So if I then multiply through by 1 over RC, I'll bring it back over here. Multiply through by 1 over RC, then I will have all of my variables separated. I'm going to keep the picture there. So multiplying equation 16 through by 1 over RC, I'm going to have dt over RC equals dq over EC minus Q. I'll put the time dependence back in, Q of T here, just to emphasize what is constant and what is not. Yeah, so that is a separated equation. All the variables and the constants associated with those variables are on different sides, and the constants have either units of charge or time, and of course the variables do as well. Now, here is where we do something that is really interesting. We define a time constant. This term RC has units of time. And so here we define a time constant that we'll talk about the meaning of it momentarily. But we define a time constant as RC. Actually, your book doesn't even do that. They just keep it as RC. Oh, no. That's interesting. Maybe they do somewhere, I'm just not seeing it. Oh, the time constant, yeah, the capacitive time constant. They don't use the symbol though. There's a symbol that's generally used for that. One moment. Right, so let's go ahead and define this time constant as tau. And I usually, there's different time constants that we can define. I'm gonna call that tau RC, because we'll have one when we get to an inductor circuit as well, do something similar to this. Tau RC is defined as R times C. And sometimes it's nice to go to and prove to yourself that the units of resistance times capacitance gives you time, units of seconds. So we can then write this separated equation in terms of tau RC. I'm going to do that from this point on. So we can have 1 over tau C, tau RC, times dt equals dq of t over EC minus q of t. So from this point, we, oh, and there's a minus sign on that. Did I drop a minus sign? No, not yet. I have to flip them around, okay. Yeah, we're good. So far we're good. Equation 19 is good. So now we have to basically integrate both sides, and the integrals are relatively simple. The left side just integrates to t. So let me do one more thing before I integrate. In order to get my signs to work out the way the functional form to get out the way I want, I'm going to factor out a minus sign from the right side of this equation. come back over here. I'm going to factor out a minus sign. I'm going to go ahead and put in the integral signs. And I'm going to do a definite integral. You can do it with an indefinite integral and solve for constants. That's one way, but I'm going to do definite integral. Apply boundary conditions to. So equation 20. So this is going to be basically dt over tau c integral. Oh, sorry. Guess we could do it like this. 1 over tau rc, excuse me, integral dt equals, and that goes from 0 to t. And this is the integral of q dq. And I'm going to flip these around, factor out the minus sign, so I'm going to have a q of t minus ec. And I could factor out the minus sign and put it here, but I'm going to take the minus sign and put it all the way on the other side. Or I guess let's just do it in steps. So then that'll go from q naught to q of t. So what we need to solve is this equation minus tau rc integral 0 to t dt equals integral q naught q t of dq over q minus ec. Okay. So the right side over here just integrates to t from 0 to t. So we're going to have, or the left side, excuse me. So minus t over tau rc. The left side, so the right side is a log, or a logarithm, but you got a constant in there. So the solution would be, and this goes from 0 to t. So the solution here is going to be the ln of q of t minus ec, and that goes from q naught to q of t. We just make that q so we're not confused on that. So q. So I'll be substituting it. Yeah, goes in. Okay. So in my notes, I think I actually did it with the variables. I mean, with the indefinite integral. Let's just go ahead and work this out. See if we can get to a solution of a similar solution of what they have. Okay. Oh, wow. So it looks like I did do it with constants and solve with constants. Okay, because I'm a little bit tired, I'm a little bit anxious about doing this without following directly my notes. But it might, let me just try it anyway. So hopefully I won't make a mistake somewhere. So, you know, like for those of you, maybe some of you haven't had, but with solving differential equations, there's two ways you can do it. You can do it with definite integrals by putting in like values, numbers as I've set up here, or you can do it with indefinite integrals, but then you have to do something called, you get constants. But to correctly solve for those constants, you have to apply something called boundary conditions. That second version is what I've done in my notes, but it's a bit more mathematical. And this version is a bit of a shortcut that physicists take oftentimes. So I think I'm going to go for it and see if I can get this the right answer. The left side is no problem. When I put in, it's just going to be this thing here. So the left side is minus t over tau RC. And over here, I think what I'm going to have is, so you know, it's final minus initial. So I'm going to have ln of, I guess, q of t minus EC. I guess maybe I should have absolute values there. And then minus ln, and I put the constant in, and that is, wait a minute, is it Q naught? What am I saying? No, Q naught is equal to 0. My bad, that's what's happening. Yeah, because, so this is, with this problem, I should have been a little bit more specific. This capacitor is charging up. So there's two versions of this problem. One is when the capacitor is charging. So I close the circuit, current goes until the charge, the current dissipates, as I said. And so the capacitor is charging up. So at time t equals 0, Q naught is actually equal to 0. That's what was throwing me off here. So I plug 0 into this thing. So when I plug 0 into here, this second term is just going to be the log of EC minus EC. But that's got to be right. Yeah. And that's probably what I did. Yeah. Right. And there, I guess I have to use that log has to always be positive, so absolute value. So I think I have to just translate it there by making that term positive. Whenever you do it with the other way, I guess I handle that minus sign a little bit differently. It comes out whenever you define the constant in a certain way. So and maybe that's just the definition of a absolute value. Yeah, so this has to be absolute value here. I think someone talked about this the other day. What's the definition? The definition of absolute value for a logarithm, a definition of a logarithm. There's something that I'm just drawing a blank. There's some, I always try to get the correct mathematical terminology or definition to justify something. And right now I can't remember, but I think it has to do with the definition of a logarithm that that this thing right here, I don't know if we said this before at some point in this semester. I was talking about some student with this in class this semester. I can't remember which class, but that thing is going to be positive, and it has to do with. So this is going to be the log then of Q of T minus EC minus the log of EC.
Professor,
Yeah.
in my differential equation class, what we did when we were doing separation of variables, is that we did it with indefinite integrals, and then once you are in step 21, you would do E on both sides.
Oh yeah, I'm getting to that. I'm getting to that.
Okay.
Yeah, I'm going to do that in the next step. I'm just trying to think what the justification is for. It's kind of a trivial thing, but it just bothers me. Do you remember was it just the definition of the logarithm, why I can just make that positive? That the argument of a logarithm can't be negative. So what does it come? That's what I'm thinking about here. It's not that I'm lost in the derivation. It's just, do you remember the justification that why I can go from the, I know you can do it, I just can't remember what the rule is, why I can go from here to here.
Well, I guess the main, or I will say the main of the logarithm, it's always from 0 to infinity. You can have a negative number on the logarithm.
You cannot.
You cannot.
Okay, so yeah, so that's why it's always written with an absolute value sign, which I should have done here in the beginning. And it's just the definition of a logarithm, that a logarithm, the domain of a logarithm. So domain is the set of all possible numbers that you could put in. So both the domain and the range of a logarithmic function are positive values. That's what it is?
Yeah.
Yeah, okay. All right, so I guess I'm overthinking it a bit. But that's all I was thinking about. I couldn't remember because I don't have, I usually write all those little details out, and I'm just kind of doing this off the cuff. But yeah, you're right. Yeah, so cool. But before we do that, we need to use, before we apply the exponent to both sides, we need to use that rule. What is it? That the log of A minus the log of B is equal to log of A over B. Remember that? So now that I have that positive, I'm cool. I can do that here. So this step is going, but thank you though. I appreciate you helping me out with that just in case. But minus T over tau RC is equal to log of Q of T minus EC over EC. Everybody remember that? Now I'm going to take the exponent of both sides because I want to, by taking the exponent of a logarithm, you factor out the argument. And by the way, Monica, the name of that thing inside is an argument. I think you were saying like the main part of the log, it's called an argument. Yeah. So now I can take the exponential of both sides of this equation. But good. So you do remember. So did you get the final solution, Monica? Were you able to work through it?
Yeah, I'm finishing up right now.
Cool. Awesome. So if I take the exponent on this side, I'm going to have e to the minus t over tau RC. And then e to the log just takes out the argument. Why don't I just, yeah. So e, so like, yeah, they're like exponential of a logarithmic function. It's going to take out the argument. So this would be Okay. So we're on the home stretch. So now it's just algebra. I can solve this for QT. And if I solve it for QT, I'm going to first divide through or multiply through by EC. So I will have EC, e to the minus t over tau, RC, equals Q of t minus EC. And taking EC over, 28, I've got Q of t is equal to EC plus EC, e to the minus t over tau, RC. Now factoring out, oh my gosh, seriously? Did I miss a minus sign somewhere? Seriously? So frustrating with that. I've missed a minus sign somewhere. Where? Ah. It's so frustrating.
I think it's the negative EC in the natural log. On 22. I think if that's left negative, it'll carry all the way through.
Oh, yeah. So is that a property? Is like the log of negative a. You mean this minus sign?
I think that's the one that needs to be negative.
Yeah, so that's negative log of a. Is that right? Is that a property?
I don't think so, but once you remove the log, it doesn't need to be positive anymore.
That would. Once I remove the log, so here, once I remove the log, it doesn't need to be positive anymore.
Yeah, so when you apply the I think what Jason said is when you apply the rule that the logarithm minus logarithm, it'll just be QT minus EC over minus EC if you leave the minus sign. And it's just carry on over to the end.
Yeah, but I can't do that. Mathematically doesn't make sense, but I do know what I have to do. You know what? That's why I don't do it this way. Because yeah, I remember now. That's why I don't do it this way in my notes. Because this is all kind of like hand waving stuff with physics. This is why I can. Yeah, okay. I can't do that mathematically. I can't just keep that minus sign in there because it's not minus, right? The log of the argument of a logarithm has to be positive, like we said. So then I just make it positive, and that's what I call hand waving. Like mathematicians don't do that; physicists do that kind of stuff. And I'm always a little bit sketchy with it. But the reason is the justification that we said with Monica. But the problem is that I didn't handle this over here. This is always also a negative quantity. Look at it. Because I'm in the region where I'm going from Q equals 0 to Q equals some value, maximum on the capacitor. So during that time period, which is where this mathematical derivation is taking place, this quantity is going to be a negative number because QT is always going to be less than minus EC. In fact, minus EC, sometimes you see this derivation, that is the maximum charge on the capacitor. And so sometimes you do see this derivation with that as a Q max or a Q whatever, I don't know. But whenever I take that minus sign off here, what I should have done is flip this around. And again, it's like hand waving stuff, but it's valid because of the same reason that I take the minus sign away from here. This number cannot be negative because logarithm is not defined with negative, range in the main. So I have to flip that around, and I forgot to do it. So I remember now. That's why I don't do it this way. And I knew I was going to do it off the cuff. I was going to make mistakes. But whenever you do it the rigorous mathematical way, which is, as Monica said, with using the indefinite integrals, you don't have to do that kind of wishy-washy stuff. It just all works out by applying the boundary conditions and solving directly for the constants. And so you don't get into that kind of stuff. Yeah. Okay. So now we're good. Now we're good. So I have to just go through every place and flip it around. So I hope that I know that I hope that you believe me. I'm not just making this up. This is actually this is the way it's done when you do it this way, and that is a valid justification. Yeah. So yeah, you guys are right. That would work out math. It would work out numerically, I guess, but that you can't just do that. If I can't just leave that negative sign in there. So it's the other one that I had to worry about. So minus Q of T, and then this is going to be EC minus Q of T, and then this is EC minus Q of T. But thank you for helping me to figure that out. Who was that? Was that Dami? Was that you speaking? Or who was that? Dami? Was that you or Shore? Who was that? I didn't turn around.
Yeah, it was me.
Yeah. So I think we're good now. So that yeah. So if I take the minus QT over on this side and take this exponential term on the other side, what I'm going to have is positive Q of T equals EC minus EC e to the minus T tau RC. So are you all happy with that justification? I think that's sometimes books say something about that. I don't think yours does. So I don't think they put the details of this derivation. No, they just write down the answers. Okay. So yeah, so now I can Q of T equals EC, and then 1 minus E to the minus T over tau RC. And that's the classic result that you get for the charge on the capacitor. And we want to graph that and take a look at what that looks like. What it shows is that the charge charges exponentially on the capacitor with time, with respect to time. So if I take a little graph of that, it's going to look like this. And here it defines, it gives the meaning of the time constant, defines it pretty clearly. So if this is Q of T on the y-axis, and this is time on the x-axis, I'm going to have a maximum current, a maximum charge, which is going to be on the capacitor at some point, it charges up to that. So this is, that maximum current is actually EC. So Q max equals E times C. And again, that's taken directly from the definition of capacitance, right? Capacitance is equal to charge over voltage. So charge is equal to capacitance times voltage. Now, because of the nature of the exponential, technically speaking, that capacitor will not be fully charged until it will take an infinite amount of time for the capacitor to charge. Because that's when this term goes to zero, is when minus t goes to infinity, technically. So you're going to have something that looks like this, where it's charging up exponentially. But what we say, that's where the time constant gets its relevance, because first of all, we can control the time constant of the circuit. We can control how much time it will take for this capacitor to charge, because we control the capacitor, the value of the capacitor and the resistance. And understanding what those values are, we're going to know what the time constant associated with the circuit is just by choosing our resistor and our capacitance. This is something that's done in the lab. We work with this a lot. It's kind of a great lab. Unfortunately, the Beyond Labs doesn't have an equivalent, but that's where you get out an oscilloscope or something like that, and you can show that curve. You get like the different types of graphs with the oscilloscope, sawtooth curve, and things like that. That's where it's coming. That's where a sawtooth curve comes from, because it's oscillating time, so it basically, on an oscilloscope where the voltage is flipping back and forth, you get something that you've probably seen these curves. You get these kind of curves. It just does it over and over again, where that's the period of one cycle. But for DC, it would just look like that. So what I was about to say is that the time constant if you work through this equation and put in tau RC, so what is the charge on the capacitor in one time constant where T is equal to tau RC? What you end up solving is, well, we could do it. Let me go ahead and erase this now. At one time constant, you get, so for T is equal to tau RC, you're going to get that the charge is equal to EC 1 minus E to the minus 1. And that ends up being 0.68. So the charge, 0.68 of the maximum charge, 0.68, because that's what that value is, times EC. So what we say is essentially at one time constant, the capacitor has charged to, sorry, not 68, 63. 63 has charged to 63% of the maximum value. So that gives you a way of kind of gauging when the capacitor, at what time, for all practical purposes, the capacitor will be fully charged. And usually that's something that's much, much less, obviously, than infinity. If it's infinity, then it's very impractical. It doesn't help us. So, 0.63 EC, Q max. So if you choose your time constant, by choosing R and C to be 7 seconds, for example, then you can pretty much guess after 2 or 3 time constants, the capacitor will be charged to the point where any variations of charge on the capacitor are going to be relatively negligible. And again, you have very much control over that because you can design the capacitor to have whatever resistance and capacitance, and therefore whatever time constant you choose based on your choice of the resistance and capacitance of the circuit. So you see these classic curves like this, and this is what it means that, yeah. Well, I guess we're about time for break, yeah. But let's have a working break. First of all, any questions about this? Any questions at all? Any questions? I want to do two things. We're going to go on a break right now, but I want to do two things. First of all, we have the charge, and the charge on the capacitor, as we say, is charging up. This is the equation of the charge. But we also can figure out very easily, now that we have the formula for the charge, we can figure out the trend of the current in the circuit. Jason told me at the beginning of this lecture that the current is decreasing. Okay, well, how? What is the functional form of the decrease in the current? Prove it. Well, now we can. We can do that simply by taking the derivative of equation 29, because the definition of current, so this would be 30, 31, so then 32. Remember, current, I of t, is defined as the derivative of Q of t. So in order to get the current, we just simply need to take the derivative of equation 29. I'm going to have you do that over the break. So I want you to take the derivative, find the current in this circuit, and where the capacitor is charging. So so determine I of t. Go ahead and draw the graph, sketch the graph of I of t, and determine the meaning of the time constant for that circuit. And the way you do that is, once you have the formula for I, you plug into I the value of the current at tau RC, and you should get something similar for current that we got here for equation 31. So that's one thing I want you to do. Continue working during the break, or whenever, like give you a working break. And the other thing is, we can now do all this over again. Remember what I told you with the capacitor is that it's very useful in that once you charge it, you can actually open the circuit and take the capacitor out, and the charge will stay there indefinitely, practically speaking. And you can use the capacitor in other circuits. In fact, what we have said, even when we were talking about a capacitor with, when we just looked at the, introduced capacitors, we said that capacitors can act like, can act like batteries. Like, let's say that I took a charged capacitor. So I've erased that picture that I had of my circuit, but let's say that I opened the capacitor. So I opened the switch, once the capacitor was fully charged, took the battery out, and then closed the switch again. If I do that, then now the capacitor doesn't have anything to fight against. Remember, we said that the reason current stops is because of the opposite polarity of the capacitor versus the battery causes them to work together. And that's why once the capacitor is fully charged, why the current will not, will stop. Go back and look at the notes on that. I think we had on the lecture of capacitors, I had some question and answering about that whenever we went through that process. Well, once I take the battery out, then there's nothing restricting the capacitor to force charge back to discharge and force current back in the opposite direction of the circuit relative to the beginning. So that's called a discharging capacitor, the problem of a discharging capacitor. The problem that we just did was a charging capacitor. But for a discharging capacitor, the circuit would look like basically just a charged capacitor in the thing and a resistor and a closed circuit. So therefore, if this were the positive lead and this were the negative, which is what it was in our capacitor, in our original, then once I close that switch, the current will flow in the clockwise direction, the opposite of what it was before. Now, it's not going to continue. It will die down to zero because a capacitor is not like a battery. You know, as long as a battery has its chemical energy, it will continue to provide a voltage. But initially, for a discharging circuit, the current is going to be a maximum value. Sorry, the current is going to be a maximum value. The voltage across the capacitor will be a maximum value, but it's time dependent because this resistor is turning electrical energy into heat by joule heating, which we defined last week or whenever it was. So as the capacitor discharges, the resistor heats up and releases that energy as heat. And so therefore, the current will die to zero as the voltage on the capacitor dissipates and as the charge obviously dissipates. So the way that you solve that problem is to do exactly what we just did for the previous problem. Go through, start by applying Kirchhoff's voltage rule to get a differential equation that you can solve, and then solve it just like we did by using separation of variables. So obviously you're not going to do all that during the break. What I want you to do is to focus on this right here. But this is the problem. I don't know if I'll do it in class, but it gives you an opportunity to go back and do this on your own because it's the same solution. Well, a similar solution. You're going to get a different answer. But it's analogous to the solution we had before. And all the steps, you can use the same steps that I worked out here to solve this problem. But for now, let's take our break. So right now it's 9:42. Oh yeah, so Angel, yeah, sorry. So yeah, that's this problem here. We can work through that if you want to, because yeah, I'm sure they do it. All the books do it. Yeah, maybe we can work through it. For now, let's get the current, because I don't think they do that in the book. They probably just do the charge, but I want to do it because it's an easy problem to do. So let's do that. And let's take let's say that give you a little bit of time. So right now it's 9:42. Let's come back. I'll give you 25 minutes or so ish. So let's say we come back at 10:05. So that give you plenty of time to work through these details. 10 o'clock, 10:05 ish, something like that. And then we'll take a look at the discharging capacitor once we get that other stuff done. All right. I'll be right here. Oh. Let's see, can everyone hear me? Angel, can you hear me? Thank you. All right, let's go ahead and do this. This current. So starting with equation 29, I'm just going to plug that into equation 32 and take the derivative. And if I do that, I have the, so 29 into 32. So my current is going to be equal to the derivative of this thing, EC, 1 minus e to the minus t over tau RC. So I'm taking the derivative of an exponential function, essentially. And what is that? So derivative of the 1 is a, so this EC comes out, it's not a, EC. Derivative of 1 is 0, derivative of minus e to the minus. Wow. Derivative of e to the x is e to the x. That's right, huh? Yeah. But there's a minus sign translation there, I think. So derivative of e to the minus x is minus e to the minus x, right? Wow. Yeah. That's right. 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 Yeah, that's right, Angel. That's what you get. You're going to get, taking the derivative of this thing, you're going to get, so remember d at d dx of e to the ax is equal to a e to the ax. So using that in here, minus sign is going to cancel that minus sign. And I'm going to have a 1 over RC that comes out. So this is going to be EC times 1 over tau, or 1 over tau RC, times e to the minus t over tau RC. Tau RC is R times C, so that becomes EC over RC e to the minus t over tau RC. So the C cancels, and then I have, I think that's what you said you got, Angel. So E over R e to the minus t RC, tau RC. Now, you can write that, you can define E over R as the maximum current, and that just comes out of Ohm's law, right? That this E over R has units of current. So sometimes you see this written as, E tau is equal to I max times e to the minus tau RC. So either one of these is going to give me solution. Where I max is equal to E over R. And if you graph that at t equals 0, so if you put t equals 0 in here, you're going to get the maximum current, right? I of I of t equals 0 is going to be equal to E over R times e to the 0, which is just E over R. And as time goes to infinity, then this whole term will go to 0 because e to the negative, 1 over e goes to 0 as 1 over et goes to 0 as t goes to infinity. So if you were to sketch a graph of this, it's like the inverse exponential function. Well, not inverse exponential function, but it's the same as this thing. Maximum current is here, and the current dies exponentially. That's what I'm trying to say. This is time. And if you put in the time constant into this function, then you get that in one time constant, is equal to E over R to the minus e to the minus 1, which is going to be equal to 0.37 E over R. Or 0.37, 37% of the maximum current. Given that E over R is equal to the maximum current. So again, it gives us some qualitative gauge of how long it takes this thing to discharge. Because if the time constant is 10 seconds, then in one time constant, the object has discharged to 37%. So then in 30 seconds or so, you could assume that it's practically discharged for that example. Yeah. All right, so got the current, we got the graph, and the meaning of tau RC for a discharging, for a charging capacitor. So we got both the charge and the current for both of these. Professor, we can't really see the board. Why not? What was that? Is that Dami? Why not, Dami? Is it what's up? Oh, it's in the light. So yeah, that's a problem. I don't know if I can fix that very well. I'm going to be able to get rid of that glare. I really apologize for that. Decreasing the glare decreases the overall light of the thing, and because of the change in the daylight savings time, it's kind of looking different than what it used to be. Maybe I could bring this in closer, but bringing it in closer is going to cut off some of it. Yeah. Better? Okay. Yeah, Angel. Yeah, I know that. That's what we're trying to get rid of. Yeah, there's no way I don't have any control over and completely getting rid of that. I apologize. So we usually have it to a point where you can see though. So Dami, you said that was a little better. Is it still okay? No, not too obstructive. Okay. Yeah, I don't have any other way of managing that. I'm sorry, at the moment anyway. So someone had mentioned the idea of doing the discharging problem. I think it's probably worth doing it. Go through this once, go through it again. So why don't you give it a shot? Why don't you go ahead and go for that? So I guess I could redraw the problem a little better. The method is that you start with applying the voltage rule to a discharging capacitor, and that would look like a discharging capacitor at least set it up. Set it up for you, and so the idea here is that you take a charged capacitor, place it in a circuit, close the switch, and the current dissipates. I've tried to keep the orientation the same as the previous circuit. So the current dissipates in the counterclockwise direction. It discharges, as I said. And so you then, you apply Kirchhoff's voltage rule, get the difference equation that you need to solve, and then go for it, solve it. Go ahead and look at that real quick. You can take a few minutes to work through that. Got a little time I can spare to do that. And should go a little bit faster. To So I'll just start you off like going around. Let's want someone. So let's see, someone who's been Monica, you did it earlier. What about Shora? Shora, can you go through this? Let's put up the points 1, 2, 3, 4, and at least apply the Kirchhoff's voltage rule to give me the equation that I need to solve. So go around, doesn't matter what direction, maybe counterclockwise or clockwise, whatever, doesn't matter. But go around, and maybe it might be best to follow the direction of current. It doesn't really matter. But apply the Kirchhoff's loop rule and to tell me what equation would result by applying the loop rule to this discharging capacitive circuit. So what I'm asking you to do is the same thing that Monica did when we started the last problem. Very first step. Sure, are you there?
Yes, I am. I'm just thinking.
Okay. Oh. Can I move you along a little bit? If you start at position 2, if you go from position 2 to position 1, and notice that's in the same direction as current, but doesn't. So is there a voltage change between from position 2 to position 1? Sure.
Yes, there is.
Why would there be a voltage change?
Oh, sorry. There's no voltage change. For some reason, I thought you asked is like is voltage like continuous? But you know, it's
All right, it's all good. Okay, it's all
no
good. So we're on the same page. No voltage change. What about from position 1 to position 4?
Yes, there's like a spike.
That's a switch right there. That's just a switch.
Switch.
Yeah, that's not a
Okay.
circuit element. That's a symbol for a switch.
Okay, but there still shouldn't be any voltage change.
No, there's no voltage change. That's right.
Yeah.
What about from 4 to 3?
Yes.
Okay, agreed. And what is that voltage change?
That is like a 0.37 like increase, or is it a
I haven't given you any values for this.
so like the equation above is not reflecting?
No, this is a new, so we've started a new problem. This equation above goes with this graph, and all of that, those are the results from the last problem where we had a charging capacitor. So this is reflective of this equation. So let me number, so 30, I guess 38, 39. So 39 is the result that we got from putting in tau equals time equals tau RC into this equation here. So it goes with that graph. All of that's for the last problem where we had the capacitor charging. What I have now done is I've taken that capacitor from the last problem out of the circuit. Basically, I took the switch, I opened the switch, I took out the battery, and then I closed the switch again. So now it's a different problem where I charged up a capacitor and I have a charged capacitor in a circuit by itself. When I close the switch, what happens, and you might have come in, I don't know when you came in, but we had talked about this a bit earlier. When that happens, now this capacitor acts like a battery for a small amount of time. How does it do that? Well, there's no voltage. You remember before we said that when there's a battery in here, they have opposite polarity. So once the capacitor charges up, it's working opposite. The polarities of the battery and the capacity are opposite, so they work against one another, and that's what causes the current to stop. We talked about that when we defined capacitors a few weeks ago. But once I take that battery out, there's nothing to work against it. So this charge will bleed off. It's what we call it, bleeds off, or the capacitor pushes current back around the opposite direction. And it will do that until it dissipates through the resistor. It heats the resistor up, but because the capacitor isn't really it's acting like a battery, but it's not a battery. It doesn't have any chemical energy, so it can't replenish its voltage as it dissipates. So the current discharges, and then it just kind of dies down to zero after a certain amount of time.
So will both the current and the charge decrease then?
Yes, they do.
Okay.
Just like in the last circuit, both the current and the charge increased. Oh, wait a minute. What am I? Well, sorry. The charge increased and the current decreased. And that was with this. But here the current will decrease also, but for a different reason. So in the last circuit, the charge increased, the voltage increased on the capacitor, and the current decreased. So this last point was what I was showing there. In this circuit, the charge will decrease on the capacitor, the voltage will decrease, and the current will also decrease again, but for a different reason than it did in the last problem. So yeah. So does everybody understand qualitatively what's happening with this circuit? Sure, you understand everything?
Yes, I understand.
Okay, so we don't have any numerical values here for this resistor, but we know that its value is, its resistance is R, and we know Ohm's law, V equals I times R. And we also know those, I guess, properties I gave you the other day for applying the Kirchhoff's rules and I forget what I call it, protocols or whatever, for how to determine the voltage across circuit elements, particularly resistors, whenever we're traversing in the direction of current or opposite direction of current. That's what you have to use here. When I ask you how much voltage will be dropped across that resistor, I want the answer in terms of the I of t, the R, and just the nature of whether the voltage will increase and decrease, or decrease for a charge going through that resistor as you traverse it in the direction that we are, in the orientation that we are keeping, which is the counterclockwise orientation. So how much voltage then is dropping across that resistor when you go from 0.4 to 0.3? Sure.
Sorry, do you mind repeating that one more time?
Yeah, it's the same question I asked you earlier.
Mm-hmm.
The voltage, you said that the voltage will change from position 4 to position 3, right?
Yes.
Okay, how much does the voltage change in terms of I and R?
The voltage would decrease. Sorry, when you say like I and R, are you referring to like the charge and current decreasing, like respectively, or are you referring to
R is a value.
Mhm.
That's the value of the resistor. I is the value of the current at any particular instant in time, particularly the instant that you're considering it. So I and R are related to the voltage drop across this resistor through Ohm's law. So what is the, so do you remember, were you in class the other day when we applied Kirchhoff's loop rule? do a circuit?
I don't. No, I was not in class last week.
Okay. What about earlier at the beginning of this class where where Monica did it, or Monica did it? Did you when we started that problem? Were you here then, or did you not? You might have
No, I
been.
kind of logged in around 9 a.m. or so.
Okay. All right. And why don't we go with someone who knows how to do this? I want someone to do this. Who wants to do this? But thank you, sure. I appreciate it. Gonna make me call on somebody? Really? Oh, sorry, I didn't see you, Dami. Dami, go for it. Yeah, do the whole thing. Just do the whole thing. Yes. I'm Angel. Oh, you might have. I didn't see that. Sorry, I keep forgetting to read the stuff. Let's go with Dami. Dami, why don't you just do the whole thing? Just what is apply the loop rule and tell me what the equation is. And you can start at between 4 and 3 if you want. But yes, minus IR is correct for that. So go and finish up.
So it'll from I can start from anywhere, right?
Yeah, you can start from yeah.
Okay. From 3 to 2, it'll be negative negative delta V plus, since the capacitor is acting like a battery, right? So from
Yes.
3 to 2, it'll be negative delta V, then plus I, then will there be a current change from 1 to 4? Or it's just because the closed circuit, it will be, there won't be any.
Yeah, this is just a switch.
Okay.
Yeah, so no voltage change. Are you done?
No. Then it'll be another positive I.
Plus or?
Yeah, plus I. Then minus IR equal to 0.
Okay, well, what are these two I's coming from? What leg is that in? Is that 2 and 1 and 1 and
First
4?
I is 2 and 1. The second I is 1 and 4.
Okay, so first of all, good effort, but this doesn't those terms don't make any sense. Once they don't have units of voltage. Kirchhoff's loop rule is a sum of voltage, right? And so you're saying there's a current in that leg. Okay, there is, but that's not this is not a sum of currents, this is a sum of voltage, right? Voltage plus current doesn't make, that's apples and oranges. Minus IR has units of voltage, that has units of amps, and voltage. So these things shouldn't be there.
Yeah, but well, the reason why I just put the I is because there was no um circuit component between 2 and 1 and 1 and 4. So it was like, unless it's just V plus that I'm putting there, I didn't know like the exact voltage equivalent to put there.
Okay, well, we can, that's good. We can work with that. Let's work with that. You're basically right there, but I think I would say maybe you overthought it. We're adding up the voltage change. And is there a voltage change between 0.2 and 0.1?
No.
No. So then there's nothing. The voltage change is 0. So there's no I that you need to place. And the reason there is no voltage change is because of what you said. There's no circuit element. And because we're dealing with an ideal circuit and we assume that the wire itself has no resistance, because if we did assume that the wire was not ideal, there would be a voltage change just associated with the wire. And it would just to give you, just to let you know that you would treat it like a resistor, and the voltage drop across that little point would be I times the R of the wire, not just I, but IR. But since we're assuming it's ideal, then it's just zero. So there's nothing there for that name, zero. And same thing for the other thing. That's just a switch, the symbol for a switch. So it's just off and on, or, it's like connecting the wires, really. So that's nothing. And so that's also zero. So the only voltage change would occur in leg, between 3 and 2 and between 4 and 3. I agree with what you did with minus IR. That is the voltage drop across this resistor. But there's a couple things you can do here. We actually know what that voltage is in terms of charge and capacitance for a capacitor. What is it? What does delta V equal for a capacitor?
Q over C.
Wonderful, yes. So that's the first thing. And what about the polarity based on, now, it's a time dependent Q, because as you told me, or someone did, the charge is decreasing on that capacitor as the current decreases, as it bleeds off. So I'm going to write this as a Q of T and then over C. Now, the other problem is that you were going counterclockwise. So you go through this resistor from left to right, or you traverse it from left to right. Remember, traverse just means you're scanning across. There's no current moving across it or anything. That's a gap. Or charge can't do that, right? It can't jump the gap unless it's static electricity or something like that. And then you just that's a different scenario. But anyway, so there's a problem with this. What is the polarity of the change in voltage as you move from left to right? Think about that again. Are you going up the potential hill or down the potential hill? And how do you know? Donnie?
I think if you're going from the negative plate to the positive plate, if you're going from the positive, I mean, if you're going from the positive plate to the negative plate, the polarity is positive. Negative, I'm sorry. If you're going from the positive plate to the negative plate, the polarity is negative. But then if you're going from the negative plate to the positive plate, the polarity is positive.
Okay.
So
Which orientation did you go?
I went from negative to positive.
Okay, so what's the problem?
It's the minus sign. It's supposed to be positive.
Yes, wonderful. Very good. Awesome. So to clean this up a little bit, this equation should be Q of T over C minus IR, I of T, times R equals 0. Okay. Wonderful. Yeah. Oh, wow, I almost forgot about that. Cool. Yes. Yes. So that is correct. Good. That's correct. Now, yeah. Now, Does everyone understand equation 41? That is the correct application. That's the equation that results from the correct application of the voltage rule going the clockwise direction around the circuit. Yeah. But we have a little bit more work to do before we start to work through that again. We have to be careful because the next step that I did in the problem was I was substituted in the definition of current so that I could get the full equation in terms of the time-dependent charge, and then we went for separation of variables. And remember that the definition of current is that I of t is equal to dq over dq dt, right? But here we have a little bit of an issue that we still have to deal with. And it has to do with sign convention. So let's go ahead and let me show you what I mean. So equation 42 will say that I of t is equal to d dt of q of t. But the problem is that the direction of our current has now changed. The orientation has changed. And before, when we had the circuit, when we were charging, we had the battery in the circuit in such a way that the current was going in the clockwise direction, right? Now this current is going in the counterclockwise direction. So we have to have had established a positive orientation. We have to make a distinction between that. Otherwise, we're going to introduce a sign error. So if we assume that the clockwise, sorry, I've mixed it. This is clockwise and the other was, no, the other was clockwise. Yeah. So if we assume that the clockwise orientation was positive, then this current now is actually negative. The value of the current is negative. Now this negative sign is not that. This negative sign is associated with Kirchhoff's rules. But what I'm saying is that for a discharging capacitor, our current, so let's call it I discharge or something, I of t is actually negative with respect to the current, that the orientation for charging or something like that. So whenever we substitute in for the definition of I of t, there's dq, we have to put in another negative sign because of that. Does everyone understand what I'm saying? And does that make sense? Yeah. So I guess the way that I can write that is when I substitute that in, I'm going to have a q of t over c minus quantity. I'll write that out maybe like that, minus dq dt, then times r equals 0. So that's that minus sign. So the differential equation I need to separate then is going to be q, basically 1 over c, or q of t over c plus r dq dt equals 0. And if you, they should have that equation in your book. So I think it was, who was that asked me about the discharging problem? That was Angel, yeah, Angel. So they should have that equation there somewhere for the discharging. Yeah, they should start with that for the difference. So do you see that in the book there, Angel? Equation 44. Yeah. And do they say anything about that orientation? Because sometimes they skip those little details. See, I have an older version, but I don't know if they write it the same. So discharging capacitor. Assume now that the capacitor for figure blah blah is full is 50 is fully charged to the voltage of the amp that the switch S is thrown from A to B so that the capacitor C can discharge to the resistor. How does the discharge current in the single loop vary with time? Equation 28 continues to hold, except that now there's no longer an imp in the circuit. The imp is 0. In this equation, we find this thing. So yeah, well, we cannot immediately solve because it contains two variables. These variables are independent related. Yeah, I don't know. They don't really. Yeah, it seems to be leaving out some details there. But anyway, yeah, if we do compare this to what we had before, I don't know what that equation number was, but you can see that there is in the end, it's not quite the same actually. You have to kind of, they said it's the same. That's not really true. The way we had it, it was, I guess I had some minus signs there. So you would have to solve. You have to take the E over, then multiply through by -1, and then that will get it in the same result. Yeah, that's a little bit of hand waving there because they don't say anything about this point, but it's important to know that. And if you just do the mathematics, you don't have to say like if they went back to the previous equation, made E 0, then said it's the same except for E being non-zero, that's not quite true. Because if you make E 0, the minus sign just naturally cancels out. But it doesn't distinguish the idea that the current is a different orientation. So if you didn't know that and didn't do it their way by just making E zero, because they don't even apply Kirchhoff's rule, they just say make the E 0. So they don't really apply Kirchhoff's rule again. So that's a little bit deceiving. That's the kind of thing that would always like upset me because if you didn't know, you wouldn't catch that. And if you then tried to apply Kirchhoff's rules and didn't do this, then you're going to have a minus sign problem in there. And then you would never know why. So just you have to be careful about little things like that. They just skip steps in these books trying to say they ain't gonna think. I don't know. Anyway, this is my explanation. So now, why don't you take a little time, go ahead and if you haven't, and for those of you who might have come late, it might be a good idea. This is a little bit easier because we don't have the E in there. So the manipulation of solving variables is going to be much simpler. I gave you a route to show you how to do it to make the convention work out. But it was a little bit more messy algebraically to do that. Here, you're not going to have that, right? You just get all the Q's on one side, all the T's on the other side, try to see if you can go through, do your separation of variables, and try to get the ultimate solutions and graph them. So take about 10, 12 minutes, go ahead and work on that if you haven't already. And then I'll go through the details with you again. So Jason, you look like, did you finish? Did you start? Did you try to do this yet?
Oh, yeah, I did.
Yeah, you had that look on your face like you're done. So yeah, I might come to you then if let's say maybe Monica, who else has finished or done this? Monica, have you done this?
No, not yet.
Okay. Anybody else completed it yet? Okay. So go ahead, take a few minutes, work on that, and then we'll come back to it again. Jason, I'm sorry, what did you say your major was again? Oh, is Jason there? Please go. by RC. And dividing through by RC, multiplying through by DT, and well, actually, there's a little bit of work there, isn't there? So I guess what we want to do is, yeah, guess I could do something like this. Take the Q of T over, or I'm sorry, take the R, so minus R dQ dt. Now I'm going to divide through by Q of T and multiply through by dt over R. So if I do that, I'm going to have minus dt over RC is equal to dq over q. Dq over q. And that's separated. And so now I can either do indefinite integrals or definite integrals. I'm going to go with definite. So that's going to go from, now it does have a q naught now. It goes from q naught, some maximum value q, to 0 as it discharges. And this goes from time t equals 0 to time t equals t. Yeah. So if I, when I integrate on the right side, I'm going to have 47. So this is going to be minus t over RC from 0 to t. And that equals the log of q, ln q from q naught to 0. Or q max, I guess you could say q naught, whatever. So it looks like in my notes I did the indefinite integral again. So I have to do this in my head, but I think that off the cuff, but I think that it's not going to be it's not going to be any issues with the minus sign there, please. So let's see. So this is going to be well, yeah, it's minus tau. I'll go ahead and put in the time constant. So RC is tau RC, and over here I get ln 0 minus ln q naught. So that gives me a minus sign. Is that going to be a problem? Maybe there is an issue.
Professor,
Yeah.
if it's discharging, wouldn't be from Q naught to 0? Because his charge has some charge.
Yeah, isn't that what I've done? Q naught to 0.
Oh yeah. No, but the upper limit shouldn't be Q naught. No, no, I think I'm confused. Sorry.
With an integral, it's final at the top and initial at the bottom, right?
Yeah.
So goes from
Yeah, I
Q
think you're
naught.
right.
Yeah, okay. Yeah. Yeah. So what's and the log of 0 is 0, right? Is that right? ln 0 is 0? What?
No, it's not defined. And the n of 1 is 0.
L of 1 is 0. Right, the log is not defined at 0. So Okay. Um, oh, my bad. Yes, brain fart. It doesn't go to zero. It goes to Q of t because we don't want to go to the end of that time. Like we're deriving an equation for the charge within the time that it is discharging. So our limit, our time is not to the point where it discharges. It's somewhere in there where there's still some charge on it. Even if we're infinitesimally close to when it is about to discharge, still it's like, you know, to make the analogy, whenever we were doing gravity, the drag problem, you don't integrate from the time you drop it to the time it hits terminal velocity. That enters a different procedure. It's somewhere within that time that you want to find um, the equation of motion, because once you get to constant velocity, there's no equation of motion, it's just constant from that point on. So making that analogy, it's kind of the same here. Once it discharges, it discharges. There's no more current or charge or anything. So we're within that time period. So my bad. So we go from Q naught to, yeah, that's the problem. Yeah, one of the things with teaching is well, for me anyway, if it's not in my notes, don't do it. If I'm gonna do it, write it out first. Yeah, so it goes from Q naught to Q of t, my bad. So this is Q of t. This is Q of t. So log. So now we're good. So this just becomes the log then of Q of t over Q naught. Wonderful. So let's see if I can finish this in 2 minutes, 6 minutes. So yeah, so now it's straightforward. So now I take the exponential of both sides. So e to the minus t over tau RC. The exponent takes out the log, so that's just going to be Q, takes out the argument, Q of t over Q naught. And yeah, so now we solve for Q of t. Q of t is equal to Q naught times minus T tau RC. But Q naught is just the maximum current, maximum charge, which is E, the mth times the capacitance. Right? Q naught is equal to Q max in the previous equation, which is a previous problem, which is just E times C. So then equation 51, the charge on a discharging capacitor becomes Q of t is equal to EC times E to the minus T over tau RC. Awesome. So there, mathematically, we get a very similar equation that we got for the current in the discharging capacitor. And if we graph this quickly, we start from a maximum value, but we come off like this, right? The charge discharges like so. And here, the time constant in this case, tau RC, is going to be where it discharges to, I guess, 37%. No, charges 67, yeah, 37% of the maximum value. Right? Yeah, yeah. So, so this is going to be 0.37 EC, and this is Q max, which is equal to EC here. Okay. And of course, getting the, yeah, so that's that. And that should be the result that you see in your book, therefore discharging for the charge on a discharging capacitor. And in order to, I don't know if they put the current in there, but to get the current, the functional form of the current, we just take the derivative again. So I of t is just going to be equal to Q prime, or Q dot, excuse me. Remember using the dot notation. Dot notation is equivalent to prime notation. Dot Q dot means derivative with respect to time. So dq of t dt. And if we take the derivative of that, we get, similar to what we got before. It's the same thing we got before, that I of t is going to be equal to, oh, we got to be careful because otherwise we get a problem. Remember that the current has got to be negative again. Is that true? Yes, the same thing that I said, we have to do that over. Otherwise, we're going to get a sign error. So you have to put in a negative because the current is negative, and then take the derivative. That generates a negative. So the negative and negative, so it's basically the negative of, I guess I should put that up here somewhere because the current itself is negative. Yeah, you just have to know that. So, yeah, I don't know. Maybe negative goes here, negative, whatever. So negative dq dt. So you're taking the negative of the derivative of this thing, of EC, e to the minus tau RC. And so in the end, you'll get the same answer we got before, which is a positive E over R times e to the negative t RC. And yeah, so the graph is going to be the same as we got before, where the current, the time constant is the time it takes for the current to dissipate to 37% of the maximum current being E over R. Whew. All right. So that's charging and discharging capacitors. Any questions about that? So is this it for circuits? Oh, the homework. This is the chapter on circuits. Yeah, this should be still on Ohm's law and circuits. This is in that chapter. That's right. So this is the completion of that, and the next thing should be the chapter on magnetism. So this is going to be. Yeah, 27, if that's what you were saying. And yeah. Yeah, RC circuits. 27.4. See what they say about that. Yeah, okay. Charging. Just happened. Okay. Yeah, so these are the results that we got. So that was for charging. This is current for discharging. And don't let this throw you off here. I don't know why they put it different here, Q naught over C, but Q naught over C is actually E. So this solution here and this solution here are the same solution. I don't know why they wrote it differently. It's the same. So that's what we just got. And of course, you see this is the charge for the discharging capacitor, which is what we just got here. And this is what we had gotten previously. So these answers, turns out the same. I don't know why they write it differently. And yeah, they just have some combination circuit there, switching back and forth. So it's all the same. So we went to capacitor's charge grows, that's what yeah. That's for charging, showed that. And that's the current. Also, they do show the current. And for discharging, go through and you can see all that stuff. All the stuff we did. Oh, so they do give a general solution. So if this is the general solution that they're giving, then they did it. They are doing it with constant coefficients. The indefinite integrals. That's the general solution for the indefinite integral. So that means. Yeah. So they show. So yeah, this is bound. So they don't normally do it in these books. So they're actually working through it. But this is a little bit different than the way I did it. This is using boundary value conditions. So this is the way I did it in my notes. You can read through that. It's worth doing if you want. In the end, you're going to get the same solution, general solution there. And you have to figure out what the constants are. Yeah. So I guess this gets into something else. I guess that's a problem. Okay. So yeah. Something else. All right. Charging. Yeah. Oh, so then they jump back. This is the derivation for the charging here. They jump back and derived it. So yeah, okay. So that's it. That's it. Yeah. So that ends basically we've gotten through circuits. So at this point, we're going to start magnetism. So before I let you go, let me switch back to the chapter to the here. So what we have to do now, we still got a little bit of work to do. Need to pick up the pace a little bit. We've got all of this. 1, 2, 3, 4, 5, and 6 chapters. We still have 6 chapters to go. All of which includes magnetism, and then the last 2 chapters are electromagnetic waves. This is a short chapter here, so we'll do it quickly. But we still got some work. We got time. So let's yeah. So let me get you back here before I let you go. Okay, so any questions about anything associated with circuits? Hope this has made sense for you. Yeah. Okay, well, I guess I will see you on Wednesday. Keep working through stuff. And I think I'm gonna go ahead and open up the homework and stuff for the magnetism, the chapters that we're gonna start magnetism on Wednesday. Just, I think I've been opening those homeworks a little bit late. I thought that the dates were, I keep forgetting that the dates aren't necessarily consistent with the homeworks and they're not opening up as they should be in the modules. So I'll take a look at that before the next class period. See if I can make some adjustments on that. But just keep reading, keep working. And again, I'm still suggesting that you're working problems in the back of the chapter itself that are not assigned. In some ways, I know those are really important. Those are kind of problems I'm working here. So that would definitely facilitate your learning just as much as the Wally Plus. But we have to do the Wally Plus for the grade, homework grade. Whatever. All right. So anything else? If not, I'll let you go.
Thank you, Professor.
All right. Thank you so much. I'll see you on Wednesday. All right. Thank you. Any questions or anything? If not, I'm going to go ahead and sign off. Hello?
I'm just trying to finish what's on the board.
Oh, okay.
Have a good one, Professor.
All right. Take care.
Yeah.
Abdul, David, are you?
Yeah, Dr. Brian.
Yeah.
Question. So last night, I was really behind on my past assignments and homework.
Yeah.
Last night I was doing it. I finished a couple of them. Is there any way you could reopen them so I could finish them, please?
Which homeworks are these?
Let me see. It will be the homework for electric potential, chapter 24.
So that's a kind of an old one though, right?
Yeah, it's kind of old.
So had I given you some time before or no? Because that due date was a while ago.
Yeah, it was a while ago.
So is that the only one?
Yeah, and page question 1, 2, and 3. Force field, Gauss law, and electric potential difference.
I'm not following you. What's the question?
It says P38, P30, chapter 21 to 22, F20, chapter 23, F20, Gauss law, and electric potential difference. They were due on April 2nd.
Those are homeworks or?
I think so.
So you, okay. I need a complete statement. I'm not sure. So you said the one homework was homework 4,
Homework
right?
4. Yeah, homework
Okay.
4.
All right. That's one homework. What is this other stuff you're talking about?
It's I think it's just question number. Question number 1, question number 2, and question number 3.
What
It's
about them?
force field, Gauss law, and electric potential difference.
What about them?
If you can, please unlock those 2.
Well, questions. There's no questions. There's either homeworks or quizzes. That's just.
Oh, okay. I think that's Q is for quiz then. Sorry, my bad. I thought it was question.
So the quizzes. All right. So it's 3 quizzes you haven't done.
Yeah, sorry about
And
that.
it's, well, like, why haven't you done them? Because they were due a while back. It has nothing to do with last night.
Yeah, it wasn't due last night. It's because I was doing like 2 full-time jobs. I wasn't really able to do it, so I just quit one of my job like last week. So
I tell you what, why don't you send me an email and have all those 4, because it sounds like it's 4 different things. 1
Okay.
homework and 4 quizzes.
Okay.
Send me an email and I can take a look and make a decision about that.
Thank you.
All
Thank
right.
you, Dr.